Good morning everyone, I hope you're having a lovely weekend so far. Welcome to today's worked exam answer video, where today I'm having a look at an AQA A-level question covering some aspects of structure and bonding in parts A and B, where we're going to be thinking about drawing shapes of molecules, and we're going to have to name and give a bond angle for one of those shapes. We're also thinking about bonding and structure in terms of the melting point of one of those molecules. And then we're thinking a little bit about energetics at the bottom, where we're thinking about writing an equation to show the formation of a particular compound from its elements. So we'll talk through, as I always do, each of the different parts of the question individually, but this is mainly structure and bonding with a little bit of energetics at the end. Now, shapes and structure and bonding and energetics are all fairly common across all of the specifications at A-level, but if you're not sure whether this specifically applies to you, please don't hesitate to ask. So, let's get started. So all of these questions are about thallium, which is possibly an element that you've never heard of, because it's right down at the bottom of group 3. So very handily they've told us that it's in group 3, so we don't have to spend ages looking for it on our periodic table. And then it says thallium will react with halogens to form many compounds and ions. And that is essentially the nice lead into this question, where we're going to be looking at 3 different thallium-based compounds. So first question, we have to draw the shape of the TL, which is the symbol for thallium, Br3 2- ion, and we have to draw the shape of the Cl4 3- ion. But to include any lone pairs of electrons that influence the shapes, and that's true for any shape. If there's a lone pair, it has to be drawn. We've then got to name the shape made by the atoms in the TL Br3 2- ion and suggest a value for the bond angle in that shape as well. And once we've drawn the 2 shapes, you'll understand why it's that one that we have to do that for and not the other one. So it's 4 marks, so hopefully it's fairly easy to see where those 4 marks are going to come from. We've got the drawing for each of the shapes, that's going to give us 2, and then we've got the name and the bond angle, which will give us the other 2. So we know thallium's in group 3, they've told us that. If you don't get told which group the element is in, that's the first thing we need to do, because that is going to tell us how many electrons, in this case the thallium, but whatever atom it is, has, that it can use in covalent bonds with other atoms. So thallium has 3. Now when we've got ions, the way that I handle the charges is I will either add or subtract from that number of electrons. So if we've got negatively charged ions like we do here, that means we're going to have more electrons that thallium will have at its disposal, which is the most straightforward way, in my opinion, we can deal with charges. If there was positive charges, then we take them off of the number of electrons that we've currently got. So because of the 2- charge, I'm going to then add 2 more electrons to what thallium has available, and 3 plus 2 is 5. Then we can think about how many of those electrons are going to be used in bonding with the bromine atoms. So we've got thallium to bromine bonds, and there are 3 of those. And in each of those covalent bonds, the thallium will share 1 and the bromine will share 1. So that is going to use up 3 of thallium's 5 electrons, and that's going to leave us with 2 electrons at the end. And that therefore tells me that in this shape I have 3 bonding pairs and I have 1 lone pair. Remember, pairs, so I've got 2 electrons left, but that means that I only have 1 pair of electrons. Now at that point, the application side has been completed, and this is where we then need to rote learn that any shape that has 3 bonding pairs and 1 lone pair will be pyramidal in shape. So it's based on a tetrahedral shape, but one of the bonding pairs, usually we draw it at the top, has been replaced by a lone pair. So then we've got 1 bromine in the plane of my paper. We've got one bromine that's going to come out towards us using the wedge, and then we've got the dashes back to the BR that's going back sort of down into the paper and into my desk. So we've got a triangular pyramid at the bottom, and then the bonding pairs come up to the thallium sat on the top, and then above that we've got the lone pair. Now for bond angles, again we've got to think about what the bond angle would be in a tetrahedral shape, which is the 109.5, and then the presence of the lone pair, because the lone pair bonding pair repulsion is stronger than repulsion between the bonding pairs, the bond angle between the bonding pairs is going to get smaller, because the bonding pairs are going to get squidged ever so slightly closer together. So the presence of one lone pair reduces the bond angle from 109.5 down to 107. And if we had a second lone pair, so two bonding pairs and two lone pairs, it would come down by another 2.5 degrees. So they're the three things I need to do for the TLBr32- ion. Drawn it, named it, and then I've suggested a bond angle, 107. We're not going to have to do anything other than draw the next one, and you'll see why. So we're still dealing with thallium. So our starting point is still 3 electrons. We've got a 3- charge this time. So we're going to then add to that 3 more electrons that it can use, giving us 6. Then in this case, we've got 4 chlorines. So we've got thallium to chlorine bonds, and we've got 4 of those. So again, if thallium contributes 1 to each, that's going to use up 4 of its 6 electrons, leaving us with 2 electrons left at the end, which tells me that we are going to have one lone pair again, but this time we've got 4 bonding pairs. Now, this isn't a combination of bonding pairs and lone pairs that you have to learn. So this is going to involve application of the shapes that we do have to know, and the electron pair repulsion theory to think about where we're going to put the lone pair. So if we have 5 bonding pairs, that would be called trigonal bipyramidal, and we're going to draw that kind of arrangement. But again, one of those bonds is going to be our lone pair. This is why we don't have to name this one, because we wouldn't be naming this trigonal bipyramidal, because we only name the shapes based on the bonding pairs. And this isn't, as I've already said, a shape that we need to know the name for. So I've got my thallium in the middle, and then trigonal bipyramidal, we've got 2 axial bonds, and then we've got 3 equatorial bonds. So I can probably draw the wedge and the dashes around the middle, because I'm not going to put my lone pair in one of those just because they're in 3 dimensions, so it doesn't make any sense to. But then we've got to think about, would I want to put the lone pair in the other equatorial position, or would I want to put it in one of the axial up and down positions? So I'll draw one of the axial positions in, because we can't put the lone pair in 2 different places. So now we've got a bit of a choice. Now lone pairs will repel bonding pairs more, so we want the lone pairs really to have more space between them and the bonding pairs. So if we were to put the bonding pair in the top axial position, it would then be 90 degrees away from the 3 in the equatorial position. Whereas if I was to put the lone pair here, where I am going to put it, the lone pair would then be 120 degrees away from the equatorial ones, and yes, it would still be 90 from the 2 axial ones, but it is further away from the other equatorial ones. So that is what my shape is going to be. Now I'm pretty sure, based on my university knowledge, that that would be called a seesaw shape, because if I turn this around like that, it looks a bit like the base of a seesaw, and then the people would sit here and here. But like I say, that is not one you have to know how to name, and that's why we're not having to name it here. So we've got to draw it, I've drawn it, and then for the other one I have named and given my bond angle as well. Okay, then on to part B. We're now thinking about thallium 1 bromide. So the 1 is the oxidation state of the thallium. So because that's +1 and the bromine is -1, we've got TlBr. It's a crystalline solid with a melting point of 480 degrees. So we have to suggest the type of bonding present and state why the melting point is high. So if we think about group 3, that's where the ladder separating in the metals and the non-metals starts. So it goes between boron and aluminium, where boron is the top of group 3, aluminium's underneath, and then we have the ladder going down from there. So boron is a non-metal, aluminium and below are metals. So if we have a metal and a non-metal, the type of bonding that we're going to have is ionic. And if we have ionic bonding, we will always have a giant ionic structure. And in our giant ionic structure, there will be lots of very strong ionic bonds or lots of strong electrostatic forces of attraction between our oppositely charged ions. And they're going to take a lot of energy to break. And that's why our melting point is high. So I am going to word that as follows. I'm going to use the formula because it's given. As I think I've said in previous videos, if you're going to use the formula, make sure you get it right, but it's going to save me a bit of time. So thallium bromide will contain ionic bonds and exist as a giant ionic lattice structure. There will be lots of strong electrostatic forces of attraction between the oppositely charged ions, which will take lots of energy to overcome. So that is almost a GCSE style question. That's how I would want a GCSE student to approach that, in terms of talking about the bonding and the structure. And then for ionic bonding, not sure why it's special in relation to covalent and metallic, but when we're thinking about ionic, there is a need to talk about what an ionic bond actually is in terms of the electrostatic forces of attraction between the oppositely charged ions. And all bonds are very strong, so they're always going to take a lot of energy to break. Now, because I've talked about forces, I've said overcome. Again, I like to see breaking bonds and overcoming forces, but they're not going to be perhaps quite as picky as I am in relation to that. Okay, so finally, part C, we have to write an equation to show the formation of thallium bromide from its elements. Now, when we're thinking about equations for the formation of compounds from their elements, we're thinking along the lines of energetics, which is one of the topics that you will cover in year 12. And one of the things that we need to know as a part of energetics is that when we're thinking about forming compounds from their elements, there's a set definition for that process. So the standard enthalpy of formation is the energy required to form 1 mole of a compound from its elements in their standard states. So that's going to help us to write this equation here. So thallium and bromine are going to be the elements that we have at the beginning. So Tl plus bromine, which is diatomic, Br2. And then the compound is thallium bromide. and we've already had the formula of that above, TLBr. Now, if I was balancing this, my preference would be to put a 2 in front of the thallium bromide to balance the bromine atoms, and then put a 2 in front of the thallium to balance those atoms out. But when we're thinking about formation, we can only make 1 mole of a compound. I mean, we can make more than 1 mole, but by definition, the standard enthalpy of formation is the energy released when 1 mole of a compound is formed, or the energy needed to form 1 mole of a compound. So if we're then forming 2 moles of compounds, that's not strictly by definition. So we have to balance it by keeping 1 mole of compound on the right hand side, and therefore in order to balance this, I'm going to need to put a half in front of the Br2. Now, it hasn't mentioned state symbols, and this isn't necessarily one where you would always be expected to put state symbols in, but I'll put them in while we're here. So thallium, being a metal, solid at room temperature. Bromine is one of the only liquids on the periodic table at room temperature. And it's important we go with the elements in their standard states, which means what we naturally find them at. As at room temperature. And then because thallium bromide, we've just said it's got a melting point of 480 degrees, we know that that's also going to be solid. Now, it might be that the mark scheme says to ignore the state symbols. That isn't going to penalise you. If it says ignore, it means literally just pretend they're not there. It's only if it then says reject, or if this is said maximum marks gained can be, it's only worth 1 mark. So they're going to be ignoring state symbols. So if you get them wrong, don't worry. But yeah, so that's how we would write an equation to show the formation of any compound from its elements. We can only make 1 mole of the compound, so therefore we've got to balance the elements accordingly. And that is today's worked exam answer video. If there is anything that I've covered, be that on shapes or more generic structure and bonding or energetics, please don't hesitate to let me know. Or if there's any other questions that you would like me to have a look at, again, please just reach out to me. Hope you all have a really lovely Sunday, and I will catch you again soon. Thank you for watching.